What about those liquid? They did not come. I'm waiting for. Let's see. They did not even inquire also. I hope they don't have any other engagement today. Usually they write. Morning they write. What about because I hope they didn't forget. What? Anyone of you run this calculation? Yeah. No? What about you?
Because when the input file has to modify the input.
You have to modify the input, right?
In Gaussian CV method, you have to
Pulse is not there. DCA is there.
use a
No. Oh, I'm not there. I have run the calculations. Anyone have run those calculations? Shiva Kumar?
No.
Why not? It will take hardly 5 minutes to get the results. Smallest one. Okay. We'll have to wait for them for 5 minutes. Why not? How much time it takes? It will not take even 5 minutes also. CID, CISD. How come you see it's not there? You see? Can you see this one?
Here is no
Huh.
So class means with that
Cross view.
class view, it is not showing a
Cross view not showing.
with calculations.
Huh.
Only DFT methods and hard work it is showing. So
Okay.
PA methods.
Let's change then. Quick calculation, energy, method, artifact. Let's do custom and then write CISD. That's all you need to do. You put it custom, then you write here CISD. That's all. Yeah. Almost everything is there. And do you ever perturbation theory? You don't know. No, completely forgot. Huh? What about you? Yes. How much you remember?
Take the solid, like there are two parts. One is the solid mode and one is the perturbation mode.
Mhm.
With the solid systems, we will use the solid system and the perturbation part.
No detailed derivation. So that's fine. That must be clear. Diksha Moksh will be joining or she's with you?
She will join in few minutes. You can start.
Okay. Yeah. She would be that she will be joining. Hmm. Did you do those calculations? CI calculations?
No, sir.
Why not? How much time it will take? You can do it with your laptop. It hardly takes 2 minutes. Very small basis,
Yes.
a small molecule like water, artifact, U-
Yes.
RHS,
Hmm.
USF, and CISD. That's all you need to do. Okay. Do the calculations, compare the results. You have an idea how
Okay,
much
sir.
time you are putting for CISD
Yes,
and how
yes.
much time how much accuracy you are improving. All the method that we are going to discuss now, you have to do at least some calculation. Look, I'm not asking to write the program. Right. Ideally, I should ask you to write the code. Once you finish Artifact, you should write a code for Artifact. That's the ideal situation. But I'm not asking that. If you are interested, you can write. It's not very difficult to do. But at least with some package, you should run those calculation and see how much why you are doing so, why you are doing learning so much of difficult theories. You get the idea. Right? About time and accuracy. All the method that we're going to discuss, you must do. Okay. So how far we have learned so far? We started with RT approximation, and then from here we modified it, corrected it with with the with the antisymmetries principle. We got RT pocket approximation. Just an approximation, right? And then this is we first do for atomic system, right? It has two parts. Uh, Immediately we got non-canonical form, and then from here we modify to get more intuitive idea what is called canonical habit, right? And with this we went for the molecule. We went for molecules, right? In the molecules, what is the difference we introduce? We introduce here finite basis, right? And then the noting that the Hamiltonian are spin independent, we did restricted Hartree-Fock. Okay. This gave us Hartree-Fock Roothan equation, right? We got Hartree-Fock theory, RHF, and since RHF cannot explain the dissociation limit, and also this is only for the system which is spin paired, even number of. For unpaired electron, we have alternate theory, what is known as UAG by Pokel and Nisbet. Okay. Here, the spin integration was done separately for each electron. There are in between what is known as ROH. Okay. If I have n number of electrons, let's say 4 electrons, you can have this is alpha, this is beta, alpha, and beta. right? If you force them to occupy in the same spatial orbital, we got RH. If you optimize each orbital separately by spin integrating for each orbital, we get ROH. What UH? What ROHF does? Let's say I have a condition where I have only 5 electrons. Right? We can have for first 4 electrons, we can have spin paired and RAH calculation. What will you do for the fifth electron? Shall I put in the alpha spin or beta spin? Right? There is ambiguity. There is a question. To answer the question, I can do one option. One option you do, you make these 4 electrons as spin paired and do RHF, take RHF function for this, and the last electron you choose arbitrarily any one, either alpha or beta. So this will be open shell. This will be closed shell. Closed shell means each atomic orbitals in space orbital is occupied by 2 electrons. Right? This together is known as ROH, restricted open shell Hartree-Fock. If I do the calculation separately for each one of them, right? If I calculate separately for this as and this separately, then this together will write as UH. Right? This has advantage. It gives a better description because we don't impose any restriction or constraint. The moment you put more restriction, the energy get higher. To get better energy, you have to remove the restriction. This is what we do. Restriction means 2 electrons, you are forcing them to occupy same space. If you force them to occupy same space, the energy you're getting is higher than the I mean it's higher than if you don't restrict them. So usually, if the system itself is not artifact kind, then UHA will give you a slightly better or slightly lower energy. However, the problem comes with UHF that the the functions are not the eigenfunction of spin operator. This we know, right? Since your electronic Hamiltonian does not have any spin, it must commute with L square and Lz. Or in the spin, it must commute with Sz operator. This must be zero. What is the advantage? We know from the fundamental theorem that if two operators commute, they have a common set of eigenfunctions. So we are doing many electronic problems. Approximately, the results we get, we are not sure about are they really represent a physical system. It's just an approximation. Okay? How to know that they indeed represent the physical system? By looking at whether the same function, that is this Hartree-Fock function, is also eigenfunction of the spin operator. This should give me small s spin multiplicity. Right? If that is the case, then I know this at least qualitatively a correct answer. Because both the operators commute, so they must share their common set of eigenfunctions. Right? Unfortunately, unrestricted Hartree-Fock determinant, the wave function from unrestricted Hartree-Fock determinant does not have this property. It does not satisfy. So energy wise, if you just focus on your energy, you will just give you a better description. It can explain the dissociation, but it has a property. The spin are not adapted. The functions are not eigenfunction of spin. However, ROHF is an eigenfunction of spin. So occasionally, if you want to do calculations on a radical, which we know as a open shell, or anion, which you know is a open shell, then you must do the calculations with ROHF if you want to calculate the spin. That gives a better description and slightly faster conversion. With this, we move to exact function, the which is natural extension of any theories is what is known as CA. Right? How do we write? We write the function, exact function, as a linear combination of a set of determinants constructed from the artifact orbitals. These artifact orbitals includes both virtual orbitals and the. So that's what we have done in the last class. We have done how to get the Hamiltonian matrix, and to get the eigenvalues and eigenfunctions, we have to diagonalize the. So this we get as something like AC equal to C. These are the coefficient matrix. Each coefficient, column of the coefficient matrix will give me the function, and this is a diagonal matrix. Each diagonal element will give me the state. And we also have seen that this cannot be applied for larger systems because computational time or cost increases exponentially. Okay, it increases drastically. So after something like four atomic system, the calculations are not practically feasible. So we have to restrict our calculation up to that level. Then, now what to do? Can we have an alternate theory or not? So yes, we have approximated CI, and now let's go to another way of another type of methods, what is called perturbation theory. So basically, there are two types of theories, mainly there are two types of theories. One is variation theory, and then the second type is perturbation theory. CI or truncated CI, artifact theory, all are variation theory. Right? The energy you get, the advantage of this is energy is get is always upper bound to the correct energy. So you know the error you get will be always higher, it's a positive number. The results you get, you can always improve it till you get the exact energy. So we know that if we are doing calculations on two different systems, both systems will give me a positive error. But on the contrary, perturbation theory knows as principal force. So let us go about perturbation theories. Let's see what we have done. There are many different types of perturbation theory. Uh, the simplest one is known as Rayleigh-Schrodinger. Right? Mokshi did not join. Diksha, do you know what is Rayleigh-Schrodinger perturbation theory? Any idea?
No, sir. I know simple perturbation theory when we perturb a system. That I
Okay,
know.
that simple perturbation theory is the Rayleigh-Schrodinger perturbation theory. Right? What you call the
Okay.
simple perturbation theory, that is basically RSPT. Other ones are more complicated. Right? For for the sometimes this gives a better conversion, sometimes other gives a better. So this is the simplest one. We'll start with this. Right? So let us do this. The principle is simple. Let's say I want to solve this problem. So what I'm going to do now is not for the electronic structure. Let's first talk about the right about the or derive the general expression for the production. For the MP2 or MP4 or molar preset, this is just the extension of it to the electronic structure. So before going to perturbation theory, I would like you to remember something that we already discussed, right? In the context of electronic structure theories, in context of artifact theory. If you remember that, we got this Hamiltonian operating on a artifact determinant. Just I'll come back to this point again and again. This, and if you take the expectation values of these, you get an energy expression which is, you remember that we have done this, uh, and if you remember that we have done this from the artifact theory, basically solve this equation if I equal to 7. Right? This is the canonical form of Hartree-Fock method. We got this to get optimized sum, right? And then we also noted this if I sum over epsilon I, we don't get the term of half Coulomb and experimental, right? That because of that half terms, this is not equal to that. Now, what we do if I take this equation, just write something like this. If I just do like this, f of I, sum over of I, I, then right side I'm going to get sum over epsilon I. Right? This can be written as with this is the energy expression. Right? This is equivalent to doing this computation. What is this? What is this artifact function? Artifact function basically is a determinant form of phi1, phi2. Okay? So if I operate f1, I get epsilon 1, and then I operate f2, I get epsilon 2 plus f3 epsilon 3 and so on. Okay? Because of orthogonality, I just get this. Now look at this equation. If I consider this function, this operator, something like is not some operator, is not really the electronic operator of molecular atom, but let's say some operator. I get this is a number, sum of numbers, right? Let us write this as E naught. Okay. Okay. What is this? You can note that this is an eigenvalue equation. But E naught is not equal to 200, right? So what we get from here, we get an alternate, you get an approximate Hamiltonian. You see, this is not Hamiltonian. This is not equal to the electronic Hamiltonian, right? This sum over Fock operator. So Fock operator is an operator, so H naught is also an operator. So we get an operator or an approximate Hamiltonian whose eigen function is the Hartree-Fock determinant. And eigen, what is eigenvalue? Eigenvalue is the sum of the atomic, sum of the occupied orbital energy. Okay. So from this, I can construct a wave function, a constant eigenvalue equation, in which I have an operator operating on a function, operating on a Hartree-Fock function, gives me a value which is, we don't know what is that, but it's a value. Okay? It's close to Hartree-Fock energy, but it's just sum of the orbital energy. And so this is an equation, eigenvalue equation involving Hartree-Fock determinant, Hartree-Fock as a function, right? So we note that this equation is very useful for us. Here we know and problem which is exactly solved. Okay. We know Hartree-Fock theory, we know Hartree-Fock wave function, and this is the sum of one electronic wave operator. This operator is a sum of one electronic operator. Right? Right? So eigenvalue function is the product of one electronic wave function. That is the anti-symmetric operator, the determinant. Right? So we know that if you can decompose a complex problem into small, I mean, many of small problem. In other words, the when the operator is additively separable, function become multiplicatively separable. Each function, each of these is a one electronic problem, which is solvable. That's what is solved, right? So from this a one electronic problem, if you construct a many electronic eigenvalue problem, we get this. So this is exactly solvable because within certain approximation. If you consider Hartree-Fock solution for one electron is the exact then but basically what I'm trying to say is this is solvable. This is solved eigenvalue problem. You can know the solution of E, right? So I can use this property of sum of Fi or H naught to go further, right, to improve this. What is left out? The left out part is H electronic, the exact operator minus H naught. This is the part that we don't know. This is the part that the eigen values or the correction for this part that is very interesting, right? This is known. Eigenvalue of this is E naught. Eigenvalue of H naught, of course, we don't know. That's the problem. That's what the problems are not exactly solvable, right? That no analytical solution is possible, right? So this eigenvalues of this E naught is close to, very good. So came from the variation theory. Right? With this small correction to this, I can get E Hartree-Fock. We know how to get from here to E Hartree-Fock, just adding that term, right? Which is like about 99%. So rest of the part, that is this operator, we need to get a correction for this operator to this matrix. That's how we are going to build future theories. Right? Many of the theories are based on that. So please remember this part. We'll come back again here again. Right? This we are going to use at this term as perturbation and H naught as a model. Right? So for the perturbation theory, let us start for the RSPT, Rayleigh Schrödinger perturbation theory. Here, what we do, this is the, let's say this is the Hamiltonian whose solution we are interested to get, but we don't know how to get them. Sometimes we don't know how to get them. Sometimes there is no possible solution also. Ideally, they should, but there is no possible way to find the solution for this. When we talk about solution, we always means finding psi. Right? E is the eigenvalue, the consequence, just a constant. Okay? But solution means psi. Let me remind you, the solution psi means why I call it called solution psi. This is basically the second order differential equation. In the second order differential equation, the solution means finding the function. Right? So you need to get the function. For the perturbation theory, the philosophy started from that. I may not know the solution of this operator, but if I know a solution of a major part of this operator, but what I say that I don't know solution of this, but I know solution of another operator, which can be known exactly. So I write now this. This is not known, or probably not possible to do, but this is known. Known means H naught is known, and all psi i's. All psi I means it's eigenfunction of a Hermitian operator, so they form a complete set. Right. So I know this psi I0 and psi J0. Since they form a complete set, they must be orthogonal. This is known. Right? And then the condition is if somehow I can write H equal to H naught plus the rest of the part. So call it V. Right? So the total Hamilton I'm writing the part that of of the known part which resemble H naught. So what H naught means? H naught means I have a system, let's say one electronic, two electronic, any electron doesn't matter. I have a quantum system which is defined by the Hamiltonian. That solution we don't know, but I can have another system which will look like or which have many properties that looks like this. Right? What is the difference? Maybe some interactions is missing here. When I have five electrons here, it also have five electrons, but some part of interaction is not there in this system, but that is there in this system. Because of that interactions, I can't solve this, but I can solve this since that interactions are missing. Right? So these two should be very similar system. It can never be like you have here five electrons, here you have two electrons. Then the systems are not same. They're entirely different. It cannot be that here I am talking about five atoms, here I am talking about five molecules. That also should not be. The systems otherwise they will be very similar. Only difference is maybe small interactions which may be present here, maybe missing here. Since they are missing here, I can have a complete exact solution to this, but not to this. If given that, and second condition that the part that is missing here, that is B part, must be very small. So this function, this system is very close to this system physically. If that is the case, then I can apply the perturbation. So what we do here, these functions, this is called a model system. Model system with a model Hamiltonian. Means that your unknown system can be modeled like a known system, and that's all. There are a lot of places we do. Commonly we do that. Let's say I want to calculate, I want to study a nanoparticle, say nano chain, one dimensional nano. This system, of course, we cannot solve it. There are a lot of electrons present, and the chain length is really large. But I can consider that as if there's one electron, which is free, and I can consider this model for this system is particle in 1D box. Right? That's how I model the system. Your Huckel theory is also a model system. We are not calculating anything about sigma electrons. We are just considering the pi electrons. So if we consider benzene, Huckel theory for benzene is just a model theory for the benzene. Right? So similarly, the structure of the system should be very similar. Hamilton should be similar. The interactions we can ignore such that the model system is exactly solved. So all you need to have an exact solution for each knot. If you don't have, we can't do anything. Right? So with this, now if I can write I write in the perturbation, I write such that I write H equal to H naught, and then I'll put the perturbation term as a lambda. I put a lambda which is known as perturbative parameter. What is signifies? When lambda equal to 0, I get H equal to H naught. I get the model system. This is exactly solved. When lambda equal to 1, I get my exact system, which is not solvable. So if I can tune my lambda such that we start from 0 and slowly increase the value of lambda till it is possible to increase, right? Then I can get close to my E. Right? What is E? E is the eigenvalues of this. Basically, I want to get this one and this one. Okay? If lambda equal to 0, I get this one. If lambda equal to 1, I get this one, which is anyway not possible. So what I do, I'll change the value of, increase the value of lambda very little, such that at certain time, whatever, I mean, to what extent is possible, I get an estimation of E, which is much better than EI naught, EI here, which is much better than EI naught, but not exactly EI, as close as possible. Right? That's the philosophy of using of the perturbation. So what we do now? Let us write the formally the expression. So this is what we are going to do. Exact theory H naught plus lambda V, we write psi I equal to EI. Now look at here. The Hamiltonian has a term lambda, as a parameter lambda. If Hamilton has a parameter lambda, the eigenvalues and eigenfunctions also should have the same parameter. The eigenfunctions, eigenvalue parameters are defined by the operator. Okay? So, since they are parameter of lambda, so I can write as EI is a function of lambda and psi I is also a function of lambda. I don't know what is the form of the function, how they are varying, that we don't know. But I can definitely tell that since the system Hamiltonian is the system is depending on lambda, eigenvalue and eigenfunction must be depending on lambda. Right? But I don't know what is the form of this. If I know the form of this, the problem is solved. We knew you cannot know that. So what to do? And we have a then the mathematical theorem, the Taylor series expansion. If we don't know a form of any function, but its form is known as a at a given point and derivative of the given point, then I can at least approximate the function. Okay? So Taylor's expansion says that if I know any function, let's say EI, I don't know this function, but I know it's a function of the variable lambda. This can be written as any given point EI naught, the value of it at lambda equal to 0. Okay? So let us write as so lambda equal to 0. Lambda equal to 0, what is EI? EI become E0, right? EI is 0. That's what we're discussing. At lambda equal to 0, h equal to h naught, and lambda equal to 0, h equal to h naught. So EI become EI naught. And then the second part is at that point I should know the value. I should note the value of the derivative of it at a given point. What is the point? Lambda equal to 0 multiply by you see this lambda equal to 0 does not mean that this lambda equal to 0. This lambda equal to 0 means at the limit lambda equal to 0 we get this value. So this is a constant, right? And then we have 1 by 2 factorial delta square EI greater lambda square at lambda equal to 0 lambda square and up to infinity. Right? This is Taylor series thing is going up to nth order. So this, if we know the values of derivative at lambda equal to 0, I can find what is EI lambda. Here is making know this. Right? If I don't know all, but at least first derivative, second derivative, third derivative, I know EI up to the side know up to second derivative. So I know EI up to second order. Right? Square of lambda is the order. If I know the first derivative of lambda at lambda equal to 0, but I don't know the rest of the part, then I know EI up to first order. Of course, I know EI not, so that is EI at the zeroth order. Like zeroth order means there is no perturbation. And then you increase the perturbation as the power of derivative, right, power of the perturbative parameter up to certain point, and you say that that order of perturbation. So if I go up to lambda square is second order perturbation, up to lambda cube, third order perturbation, and so on. Right? Similarly, I can also write my wave function psi I lambda. Same way, I must know the form of function at lambda equal to 0, which I know. Okay, this is the model of eigenfunction of the model operator, and then I must know delta E, delta psi I by delta lambda at a given lambda point and 2 factorial square psi square all at all are constant, meaning that their values are determined by an at a given. So this we know, right? Now look at here. What are these terms? These are just constant. Not only that, these are also constant. The second derivative at a particular point. So of course is a constant, right? Finally, since they are constant, these two can be combinedly written as a unique constant. Okay? So what I'm going to do here, let me write this just in modified way, but they're basically same. Ei lambda ei naught plus this I'll call as e I just in notation ei of 1, meaning that the first derivative of ei at lambda equal to 0 plus I write ei ei 2 lambda square and similar with ei 3 lambda cube. See what is lambda ei 2 this term is 1 by factorial 2 delta square ei by delta lambda square at lambda equal to 0. Right? This lambda equal to 0 specifically tells us this is a number, it's just one number. Similarly, this is a function, derivative of function is also a function, and functional value at lambda equal to 0 is a constant, the number. Right? Number divided by number is another number, just a constant number. Right? So that's what we write. Okay? And the next red color expression also can be written as psi I of lambda. I write as psi I of 0 plus I write as psi I of 1 lambda plus psi of 2 lambda square psi of 3 lambda cube and so on. Okay. This note is connection here. This is psi of and so on. Right? So what is this? This is just shorthand notation of writing the previous two expression. It means that Ei of n means that 1 by factorial n delta n e I delta lambda. Okay? Similarly, psi I of n is equal to 1 by n factorial delta n psi I by delta lambda. This derivative is short and notation I have used for this. Okay? Now these two you write in this equation. What you get here? You get h naught plus lambda v psi. What is psi? You write the whole expression. Psi I naught plus psi I 1 lambda plus psi I 2 lambda square. Okay, this is left side. Right side what we get? Let me write in the next line. I get EI. What is EI? EI is EI naught EI of 1 lambda multiplied by the same term psi I naught plus psi I1 multiplied by lambda plus psi second order multiplied by lambda square. Right? Now, both the left side and right side are equations, right? Are the terms that are powers of lambda. Right? That is fundamental theorems. I'll tell you it's easy to understand. If I have something like a0 plus a1 x plus b1 x square equal to b0 plus b1 x plus b2 x square and so on, then by inspection it automatically means that a not equal to b naught, a1 equal to b1, a2 equal to b2. So, right? If two functions are equal and both the functions are the polynomial of different power of x, then each power, the coefficient of each power of x must be equal. Right? If I have x equal to bx, it means a equal to b. If I have 5x plus, if I have 5 plus x, something like this, equal to c plus x, it automatically means that 5 equal to c. Okay, so each power of x, the coefficient of each power of x must be set. Okay. So that property are going to use here in this equation number 1 to get different terms of different coefficient of power of lambdas. So first thing we do, we say the what are the constant terms, meaning the without lambda, right? So what are the terms? Can you say the left side? You can immediately deduce to, you see this is this multiplied by this does not have any power of lambda. So I can write like h naught psi I naught. That's the left side. That's all. Everything else will come with at least power of 1. At least maybe power of 2, 3, 4 up to n. Right, up to n to n. And then right side what I get? Same expression. Pi naught psi I naught. This is the terms that from both and left and right side are without power of lambda. Then what we got? For the power of 1, lambda power of 1, you can understand that this multiplied by this has a power of 1. Right? So I get here h naught psi I of 1. Also, this power multiplied by this have a power of 1, lambda to the power 1. So I get this plus v psi I. Can you see anything else on the website? V psi I naught. V psi I, yes, psi I naught. V psi I naught. Is there any term? Is there any term from the left side? This multiplied by this, what I get? Lambda v psi I naught. I have lambda. Okay. This multiplied by this, what I get? Lambda h naught psi I naught lambda. We are taking the terms we have lambda. See this whole thing multiplied by whole thing. Right. So first thing I get the term that does not have lambda. Second term I get which has lambda power 1. Then h naught multiplied by this will have lambda power 1. What I get? H naught psi I 1 lambda. This multiplied by this will have lambda power 1. I have lambda b psi I naught. Okay.
H naught, H naught, and psi I1,
Hmm.
then B psi 0.
Psi is
Psi is 0.
lambda I'm not writing because there's a power of 1. Both sides have power of 1. I'm not writing it. Right? Provided lambda is not equal to 0. Of course, lambda equal to 0 means that is not perturbation. Right? And then right side what I get? This multiplied by this. Right side I get ei naught psi I of 1. That's what I get right side. Also I get this multiplied by this. I get ei of 1 multiplied by psi. That's all. That's all the power of lambda 1. Lambda 1. Right? Now let's go for the lambda power 2. At least 3 will write and write up to n number. Let us write three. So next we will be getting lambda power 2. What is lambda power 2? This multiplied by this will give me lambda power 2. Right? So I get h naught. Write in other color. I get h naught by 2. That's all we get. And then another lambda square. This multiplied by this the lambda square. What I get here? I get v phi I 1. There anything else on the left side? No. Right side what we get? E naught psi I 2. And then I get ei 1 psi I 1. Right? What else I get? I get ei 0 psi I. No, no, no. Sorry. Ei 2 ei 2 psi I. Right? You see there's a pattern. Right. Of course, that's what I find here. Right? What is the pattern? The power of lambda is same for each. First one there is zero, second one power of lambda equal to one, third one is two, and so on. Right? For the third term, fourth term also you can write like this. Right? Left side you have always two terms, right side will have more number of terms. Now let us explain this. What does this means? For the first equation means what does this means? This means that we are right on the right track. Psi I is not psi I not equal to ei not psi I not. That's what our model Hamiltonian is. Model system is. So we get back our model equation for the model system. Right? What does this give? This when we are going to find solve the for this problem, we get either this one, if we are to focus on psi I naught, the first order correction of wave function, or if we focus on ei naught, we get first order correction of the energy. Similarly, this will give me a second order correction of energy and second order correction of right. So that's what we're going to proceed, right? So we are going to do order by order. If I up to second order, then it is second order perturbation. If we restrict ourselves up to here, we have first order perturbation here and so on. Okay. So now let us try to find out the solution for this. So this is equation number 2. Let us put equation number 3 and let us put as this as 4. So for you see equation 2 you don't need to solve. It's already known problem. It's model Hamiltonian. We know the solution for this. Equation 3 to solve equation 3 what we should do, right? We will project with psi I naught. Right? Before projecting this, let us analyze the nature of functions. So what is a function? My exact function then will become equal to psi I0 plus psi I of 1 plus psi I of 2. Right? Why? Because at lambda equal to 1, if you put lambda equal to 1 here, my psi I is equal to exact psi I, right? Psi lambda equal to exact psi I. So that's the executive function. So executive function can be obtained by putting lambda equal to 1. If you put lambda equal to 1, that's all you get. Psi I naught plus psi I1 plus psi I2 and so on. Right? So that's the wave function. Now the same property we are going to find out. What is the property of this? If we consider this is equal to 1, then we cannot consider psi I not equal to psi I equal to 1. There's a problem here, right? Your model Hamilton and model system, the solution of model Hamilton is also normalized to unity. If that is normalized to unity, then this cannot be normalized to unity. Right? Let me write, to explain this, let me write this as a part, let's say, called chi I prime plus psi I naught. What is I here? I'm writing I. Can you see what is I? I'm talking about I. Started like psi I naught. What is I? What does I represent? I represent a particular state, the state of the system. I, if I equal to 0, or the lowest one is the ground state of the exact problem. I equal to 1, or second state is the first second state of the exact problem. Right? This I forgot to tell you. This theorem is applicable when I is non-degenerate. If 2I has same E, then we cannot apply this perturbation theory, this type of perturbation. We can have a modification to that. Okay? We have we have degenerate perturbation theory. We have multi-reference perturbation theory. We have many things, right? But the one that we are deriving now, assume that psi I is non-degenerate. There is no 2I that give same energy. So we must keep that in mind. So I can write this function as this multiple plus all other terms, right? That all other terms I'm writing as chi I prime. Some functions, right? Function plus function give me a new function. So I'm writing this plus all other terms. Then right side also I can write psi I naught plus the term chi chi prime. I hope this is clear. See, this is a total function, right? This is a total function. Is it clear up to this point? Into 1, lambda equal to 1, I get exact and then I get exact function. So I can write exact function as this. Right? What is this? This is this plus other functions. Right? So the other function together I am writing as I. No, we don't know what is it. Let us not bother about what is for time being. We can just write total function is is the model function for ith state plus some terms. Right? Whatever they are first order term, their second order, their third order, their up to nth order. Right? But it is a part of the total wave function. That much I can write. Right? Now if I write this, what I get here psi I prime, psi I naught. Let's do this kind of thing. What I get is 1, 2, 1, 2. I can write this I prime I Right. And the last term, psi I naught, right? What is psi I naught? The eigenfunction of H naught. Right. What is psi I naught here? H naught, psi I naught equal to E I naught. H naught is a Hermitian operator. So eigenfunction of this Hermitian operator also orthogonal. So I can write psi I naught, psi I naught, naught. What is the problem? This is equal to 1, but then this cannot be equal to 1. Yes? What we do here for this case, just like we have done for CA, we call it as intermediate number. Right? So in that case, what is this? This function, that is model Hamilton function, is orthogonal to the rest of the part of it. So these terms, we, because of intermediate or normalization, these two terms we consider them as, right. So part of wave function, the zeroth order wave function is orthogonal to the first order, which is orthogonal to the second order wave function. Each one is orthogonal to the other. And this is, you don't know what is that. This is just a term, a constant, it's a vector, right? It is a norm of a vector. The norm of a vector is a number, right? So the total normalization constant for the exact function will be 1 plus some term, let us call that delta, which is, you don't know what is that. You really don't need to know what it is. But this property we must remember. The total wave function, the exact wave function is not normalized to 1 if the part of it is normalized to 1. And this condition is what is known as an intermediate normalization. Right? So all we do is here, I can say that means psi I naught, the overlap between psi I naught to any nth order correction is equal to 0. This part is 0, right? If this part is 0, what is this part? This part is this plus this plus this. So I have h naught multiplied by norm of h naught and this must be 0. Norm of h naught and this must be 0 and so on. Okay? So this condition, and also I can have E I naught psi I, this is equal to. Okay? These are the condition for intermediate. So this we must remember, we are going to use this. And then let us first solve for EI naught from the equation, from equation 3. Right? What we do? We will project this equation both side by EI naught, apart from by psi I naught. If we do, let us see what we get. This is what we get. We get psi I naught H psi I 1. Right? Let us write this. We get from equation P, we get psi I naught is psi I 1, right? Can you tell me? Any one of you? The next one. V psi I naught equal to psi I naught EI ei0, psi i1, yes, psi i0, ei1, psi i0, right? Let us write this. You see, this is h naught, right? This is h naught, not h. Now see, hi, if you consider this to the right side, this is not eigenfunction of that. However, this is eigenfunction of h naught, right? This is Hermitian operator, so it can act on both bra vector and kth vector. If you operating on the bra, what you will be getting? You will be getting ei naught. What I mean that I have h naught psi I not equal to ei naught psi I naught. This is same as psi I naught star is not equal to ei naught. Right? Why I am not writing ei naught star? Eigenvalue. Why is eigenvector the condition? Hermitian operator. Eigenvalues of Hermitian operators are real. So since they are real, there is no ei star. Right? So I can write this as ei naught psi I naught psi I1 plus, we don't know this, we have to evaluate this term. What is this term? The integral, right? If you know psi I is a function, and this means integration of psi I1, psi I0 star v psi 0 beta. Okay? In the integral notation, what is this? Ei is a constant, ei naught. I have psi I0, psi I1. What is this? Ei naught is also one is also a constant. I get psi I0, psi I0. Fine. Now you see what is this? Through independent organization, just now put the condition, right? Ei naught psi I n, psi I1, it must be 0. So I get this is equal to 0. We have to calculate this. What is this term? Again 0, right? So this again becomes 0. What is this term? Ei. Ei, right? So we got a expression to calculate or to compute or to estimate the first order energy. Right? Very important. If you want to know the first order, what is telling us here? If you know the first order, if you want to calculate the first order energy, then you don't need to know the first order. On the left side, there is no first order wave function, there is only zeroth order. So if you know a model system, you can know if the energy expression up to first order without even attempt to solve it. Just get the expression values of the perturbative Hamiltonian perturbation part with the zeroth order wave function. Right? Okay. Now let us do for the second part. Right? What we get from the second part? What we are going to do here? You see how to approach this. In the fourth equation, I want to get EI, which is attached to, which is attached to E psi I 0. Right? If I want to get EI2, then I must get a project with psi I 0. Right? We need to get the norm of psi I naught. Let us do that. What we get from here? From equation 3, projecting equation 4 by psi I naught. What we get here? Is equation 4 only, right? What we get here? Can you tell me the expression? Psi I naught H naught, not square, psi I 2. Square has different meaning. Okay. And then this psi I naught E 1 equal to psi I naught psi I 2 E I naught. Can I write like this? Then psi I naught psi I 1 E I 1 plus Lopa? Yeah, yeah, I'm in class, Lopa. Can you call your mother? What? I naught right? With the same argument, I can write here as EI naught psi I naught psi I 2 plus psi I naught V psi I 1. You see right side, this term is 0, this first term, second term is 0 because of intermediate normalization. Only surviving term will be right side as EI. In the left side also, the first term equal to 0, right? So all we get is psi I naught V psi, right? There's the energy expression. There's a correction for the or for the second order partition theory, single order partition united. However, we don't know what is psi I naught. That is fine. Okay. We know only psi I is psi I naught. We don't know what is psi I. So if we don't know what to do, right? As a linear combination of a set of functions, right? You see, this is equation number 5, let's say, or 6. That will do. First order I put as 5. So what we do? Let us write this psi I on as a combination of linear combination, right? Ci, but we will not write this. There's a problem of writing this here. What is the problem? See what I'm doing here basically. We are correcting on psi naught. Let us not forget our main goal. What I'm doing here, we had model Hamiltonian psi I naught for ith state, which is non-degenerate, from the that psi I naught from the model Hamiltonian model system we know psi I naught, and then slowly we are adding the correction to it by first order, second order, and third order to improve it to go to psi I, the exact one. So I am correcting first the psi I naught, right? So this psi, and from there the part, if I put it psi I 1 and then psi I 2 and so on. If I writing this as a linear combination of this, then I must not include ith state. Understand? I am trying to correct psi I naught, then psi I1 should not be included psi I naught because that's already there. Since it's already there, I should not count it, I should not take it twice. Right? So I will not write psi I here, I will write psi j provided j is not equal to I. Right? This small part you must remember that I am correcting on psi I naught by writing psi I equal to psi I naught plus psi I 1 and so on. When I am writing psi I 1 as a linear combination of set of functions, then I must not be there. It is already there one time, it's already there here. So if I write like C1 psi I1 then psi I1 and plus psi I1, again I am getting more psi I1. Why shall I do that? Right? That will not give me a desirable function, unphysical results. Right? So you must remember that j is not equal to I. Okay, and then what to do? From the equation number 3, you put in the equation number 3 here and solve it to get psi I 1. Right? Let us write that. What is equation number 3? Let us write it as equation number 3. Psi I H naught psi I 1, right? Not 3, question number, not 4, number 3, psi 1. 1. So I write as a this is Cj psi j0. This is I am writing as j Cj psi j0, right? And then what is the next term? V psi I0. The next thing, I0 psi I1. I write as j C J I psi j0. Right? The order is always preferable to write it in a bracket. And then EI 1 psi I. Yet what we need to do here? We need to find the unknown. And what is unknown? Cx. EI is known by this time. We know how to evaluate EI. EI1, right? EI1 is known. What is unknown here? The combination coefficient. We don't know what are those. We have to find out that. So final expression for this. How to find an expression for this? For a project, a member of psi j. Right? Any member. Now let us project with psi I. Right? So if I do that, what I get here, if I now do by projecting psi I0, why I am projecting this? Because I know this I0 is orthogonal to psi j. They are eigenfunctions of model Hamiltonian. They are orthogonal to each other. So I can write H naught, oops, sum over of j Cj psi j naught, right? Plus I have psi I0 b psi I0. Right side, what I get? I get sum over of j Cj psi j naught plus ei1 c, I'm sorry, this psi I naught. Oops, not responding. Yeah. So this I can write as psi I naught, psi I naught, right? Okay, it's just a consequence of the of just write the next line of it. Now you see what you get. These are the numbers, right? I can write sum over of j outside. What I get here? I get Cj psi I of I naught is psi j naught plus what is this gives us? This gives us the same thing. Psi I naught b psi I naught. What this gives me? Pi naught sum over of j Cj psi I naught psi j naught. What this will give me? This give me Pi naught. Did I make some mistake? No, I think I made a mistake here. I made a mistake, a small mistake. I don't need to project with psi I naught. Let me put it some any other anything else other than psi I naught. I'm not going to involve psi I naught at all. What I'm going to put anything else. Let's say put psi m naught, any other state. I have infinite number of state. If that is the case, then I can put any state m, right? Then what we get here? Now you see these are orthogonal. The eigenfunctions of modern Hamiltonian is Hermitian, so this is orthogonal, so this is equal to 0, right? Just to get 0, because I don't want to get this again unnecessary thing. If I you can remove some variables, some parameters from the equation, that will be easier to solve. I have less number of unknown to get. Right? So from that, let us write this equation. What I get from here, see what I get from here is sum over of j Cj. This can operate in left side or right side, doesn't matter. I get epsilon E of J naught, right? Psi M naught psi J naught. Okay. What I get from here? I don't get anything else other than the same numbers. Psi M naught E psi I naught. What I get from here? J naught, right? What is this term? Can somebody tell what is that term? Let me write it. I'm sorry. This should be equal. Let me write it. Sum over of j Cj psi n0 psi j0, and that 0 multiplied by something is equal to 0. Now can any one of you tell me what is this guy and that guy? These two we got same. What are they? One is zero, one is some value. Out of this either both are correct or both are wrong. And any one are correct or both are wrong. What is that? Anyone from your side, Mokshi or Diksha? What is the value of the term that is red underline?
Sir, it will be
Yes,
1 when m is equal to j.
it's 1 when m equal to j. Else it is 0. Right? So I can get only Cj or Cm. That's all I can get. Right? So what this will give me? This will give me this, that sum has gone. There's no more sum here. So did I make any other mistake? Did I make any other mistake here? No, fine. So what I got from here? I got here as, let's say this m is not equal to j. This is j, right? This one is also j. What I got from here? I got here as, let's say, c of m. No, there is a small mistake I am making. What is the small mistake? This is psi I1, right? This side also psi I1. There is a small part that is missing. Cj psi j0. This is aicj psi j0. No matter. Get to get. No, this is fine. That's fine. Where is size one? Yeah, size one I'm writing as, let us write this. I'm just, it's too, I think more than an hour. I have em0. This term become 1 plus what I get from here. I get from here as, yeah, I think I'm right. There's nothing wrong I have made. Psi m0 b psi I0 equal to ei0. What is this? This will be just Cm, right? That's all we got. Everything terms, everything else will become zero. I when I equal to m, j equal to m, it is equal to 1. Else they are zero, right? So now you write this. Take what is we are interest we are intent to do. We are intent to find out Cm. So let's take all Cm to the left side and everything else to the right side, right? Then what you get? This become Cm into Em0 minus Ei0 equal to minus psi m0 b psi I0, right? I can write this as Cm equal to minus of right? You can see this can be written as right. What is the condition here? What is the condition here? M should not be equal to J, equal to I. That's the condition, right? You remember when you were putting the expansion of Ci, M was not or J was not equal to I. Right? And obviously this also get our desirable expression because if M equal to I, denominator becomes 0 and everything becomes infinite. Right? That should not be there. So what is the first order in a wave function then? Then I get psi I of 1 equal to sum over Cj, right? So I can write, I actually, not a mistake, but I should have written not M but I, J. Let us write this. It will become more, just correct it. I mean, it's not a mistake, this is just a, I mean, if I write like J, write J, it become more easier to follow. Remember, it's not a mistake. It's just an index. Oops. What I am trying to do here, replace your J from this line, M from this line onward as J. The reason is we have started with J. Anyway, little issue with my screen. Now I want to tell you that just replace M with J just to become consistent with our notations. As I said, they are not really mistakes. It's just more convenient. Always just replace wherever you have M from this line or from the red colors, then it will become stop. Let us finish it quickly. I have J. Oops. J. This is J. This is J. CJ. CJ. Just replace your name with J. Right? And therefore CJ equal to, I can write directly psi J 0, V psi I 0, V J 0, V I 0 minus 0. Right? And then I have psi I1 equal to the sum over of Cj, j is not equal to I, right? Psi, psi j naught, right? Then like this, what is Cj? Cj is this, right? So I have psi I and psi j naught, b psi I naught divided by b I naught minus, and this guy will be there, psi j. Right? So that's the first one. To get the second order energy, what is the second order energy expression? Just let me finish it quickly. I have EI2. What is the expression for that? Psi I naught V psi I1, right? Now put this here. I have psi I naught V, right? What is this one? This one is sum over J not equal to I psi J naught V psi I naught, right? Divided by EI naught minus EJ naught psi J naught. This is sum. I can take sum outside. J not equal to I, right? What is this guy? The integral, right? Integral is integration, is integral, finite integral, is a number, right? So I can write this as, this is a number I can take out. This is EJ naught B psi I naught. What is this? The bra vector operator and the kth vector. I have psi I naught V psi j naught divided by ei naught minus ej naught, right? Now see these two terms, among these two terms, this one and this one, they are complex conjugate. They are just complex conjugate, right? So what we got here, sum over of j not equal to I, which is very important. I am correcting on I, so my expression should not have I, right? Then I can write this as modulus of psi j v psi I square. A number multiplied by complex conjugate is modulus of square, right? Square modulus of that divided by EI minus E. This is the energy expression for the second order term, and we have a lot of physical significance for this, which we will be discussing in next class. Right? But note down this expression, and we'll have some physical significance of why this term looks like so, and what will happen if it is not like this example. Any question?
So the final energy term EI naught minus EJ naught will be there.
EI naught minus EJ naught. Yes. Yes. I forgot to put the naught, right? They are not. Yes. They are the. You see what we are going to getting here. Everything in terms of is also not. Everything in terms of the solution of model Hamiltonian. Nothing is unknown. Everything is known here, right? That's the important part. What happens if EI naught somehow become EJ naught in case of degeneracy? They become infinite, right? For vibration, this is called the Fermi resonance or vibration. Right? Some state do become degenerate in space. Right? You see what is EI and EJ? EI is the lowest energy. If we focusing on the ground state, EI is the lowest energy. So EJ is always higher than that. Right? The numerator is a model of square. That's a positive. Denominator is negative. So E2 will be always negative. It will improve the energy, always lower the energy. Okay. All those things we discuss in the next class. Any other question? Okay. If there's no question, we'll stop here. We'll meet on Tuesday, right? Tuesday we have a exam duty.
Two exams.
You have two exam. I have two exam duty on Tuesday. We can meet on Thursday, next Thursday.